Let's talk about solution sets of linear systems. Solve the system x plus y plus z equals 0, x minus y minus 2z equals 0, 3y plus z equals 0. A system of equations like this, where these constants on the right side are all 0, is a homogeneous system of equations. It's of the form ax equals 0 if we write it as a matrix equation. Okay, so here's our system of equations. When we apply Gaussian elimination, we end up with this. X plus y plus z equals 0, y plus z equals 0, z equals 0. You can probably see what the solution is going to be. If we apply Gauss-Jordan elimination, we get x equals 0, y equals 0, z equals 0. So of course the solution is 0, 0, 0, which is the trivial solution to a homogeneous system of equations. Anytime you have a homogeneous system of equations where these constants on the right side are 0, 0, 0, 0 is always going to be a solution. So we just call that the trivial solution. Express the solution as a vector. Okay, so again, we started off with x equals 0, y equals 0, z equals 0. So there's our solution. X equals xyz is 0, 0, 0. Let's solve the system x plus y plus z equals 0, 2y plus 2z equals 0, 2x plus 6y plus 6z equals 0. Okay, the reduced row echelon form of this matrix is going to look like this. So again, you get this matrix in augmented form. You look at the reduced row echelon form, you'll end up with this. The solution is going to be x equals 0, y plus z equals 0. Again, this is x equals 0. This is going to be y plus z equals 0. So x equals 0 and y equals negative z. That means z is a free variable. Express that solution, x equals 0, y equals negative z, z is a free variable, as a vector. Here's how we could do that. Solutions x, y, z equals 0, negative z, z. Because again, x is 0, y is negative z, and z is, of course, z. So the free variable z is just equal to z. We can factor out the z, and then we get z times 0, negative 1, 1. So this is fine. You could write the solution in this way. You could write the solution. So, I asked for it as a vector, so you could just write it in this way. I'd be fine with that as an answer. For some reason, some textbook authors don't like having a z in there. Instead, they replace it with a t. So instead of z times 0, negative 1, 1, where z is a variable, they have t times 0, negative 1, 1, where t is a variable. I don't know why they do it, but they do it. And the authors call this the parametric vector form. Okay, find a non-trivial solution to this homogeneous system of equations, a solution that is not 0, 0, 0. So again, we're looking at this system of equations here. Find a non-trivial solution. Solution's going to look like this. Again, it's going to be of this form. So you just pick a value of z. Go ahead and shout out a value of z. I think I heard you say 3. Okay, so you plug in z equals 3, and you get x, y, z equals z times 0, negative 1, 1. In other words, 3 times 0, negative 1, 1, or 0, negative 3, 3. And if you plug 0, negative 3, 3 into that system of equations that we were talking about a moment ago, you'll find that it's a solution. The homogeneous equation ax equals 0 has a non-trivial solution if and only if the solution has at least one free variable. That's where the non-trivial solutions come from. Because of course it's going to have 0, 0, 0 as the trivial solution. But if you've got a free variable like this, well, you can just plug in different values of z, and that will generate non-trivial solutions. So again, that homogeneous equation has a non-trivial solution if and only if the solution has at least one free variable. Solve this system, x plus y plus z equals 6, 2y plus 2z equals 10, 2x plus 6y plus 6z equals 32, and express the solution as a vector. What I want you to notice is that this left side is the same as this left side. So let's see if there's some relationship between the solutions. See, these are all zeros here, whereas in the one I'm asking you to do now, they're not all zeros. Okay, our augmented matrix is like this. 1, 1, 1, 6, 0, 2, 2, 10, 2, 6, 6, 32. The reduced row echelon form looks like this. 1, 0, 0, 0, 1, 0, 0, 1, 0, 1, 1, 5, 0, 0, 0, 0. So our solution is going to be x equals 1, y plus z equals 5. In other words, y equals 5 minus z. And here z is a free variable. Okay, I asked you to express this as a vector. So here's our solution. X, Y, Z equals this. 1, 5 minus Z, Z. In other words, it's 1, 5, 0 plus 0, negative Z, Z. You can factor out the Z and get this. 1, 5, 0 plus Z times 0, negative 1, 1. Or you could replace that Z with a T. Why you'd want to do that, I have no idea why, but some textbook authors like that. You get 1, 5, 0 plus T times 0, negative 1, 1, where T is a variable. Notice this is the same as the homogeneous solution plus a constant vector. Remember? Okay, when we were dealing with this, so this system of equations has this as the solution. Okay, 1, 5, 0 plus T, 0, negative 1, 1. When we were dealing with the same system of equations, the homogeneous equivalent, the vector that was the solution looked like this. Okay, it was T, 0, negative 1, 1. So here's the upshot. The solution to the non-homogeneous system is the same as the solution to the homogeneous system. You just have to throw in a constant vector. Here's another way to put it. The general solution to the matrix equation AX equals B is a particular solution to AX equals B plus the general solution to AX equals 0. So in other words, this is one particular solution to the non-homogeneous system, and then this was the general solution to the homogeneous system. So again, the general solution to AX equals B is a particular solution to AX equals B plus the general solution to the homogeneous system, the corresponding homogeneous system, AX equals 0.